Okay, good morning everybody. I hope everyone's having a wonderful day. So today I'm going to be talking more about recursion, and depending on how much time we get, we might start talking about our first sets of data structures. So just as I want to pick up from where I left off last day. So last day I defined the idea of the Fibonacci numbers for you. This is a pretty common number sequence. And the idea is that every successive sequence index, so if I were to start off with the first two Fibonacci numbers, say the first Fibonacci number and the second Fibonacci number, at least the way I've defined it here, they're 1 and 1. To get the next one, it's always by adding the two previous ones. So if I want the next one here, it would be 2 because it's 1 plus 1. Can somebody tell me what the next number in the Fibonacci sequence would be if that's the case? It's 3, yeah, 3. How about after that? Yeah, 5. One more. Give me one more. 8. You're very good, very good. See, everybody's on the ball today. What a lovely Monday. So let's get on this. So we have an idea of how this works. It's written recursively like this. It's a very natural way of thinking about. Yes, you can keep going. You get 13, so on. So I thought I would write out the pseudocode, a way of writing out the recurrence relation as an algorithm for computing the nth Fibonacci number. So question. I have two things here that seem of interest. Can you tell me which is the recursive case versus the base case? So tell me what 1 is and what is 2. So far I got 1 for base and 2 for recursive. Okay, I'm going with that. I think that makes sense, right? Because remember, when n is less than or equal to 2, I know the answer. It's 1. In this case, we're going to call the recursive case for sake of our discussion. Notice that it has 2 recursive calls. The answer is defined recursively. So we have 2 recursive calls. They represent 1 smaller, 2 smaller. So for the input. So I want to figure out what the n minus 1. It's weird to say these things sometimes. I want the n minus first Fibonacci number and the n minus second Fibonacci number. But one thing I do want to mention for you is that I can always rewrite the base case in terms of 2 if statements if I wanted to. If I wanted to have it where it's n is equal to 1, then I can have else if n is equal to 2. That would just mean I've explicitly written out 2 base cases for you. Hopefully that's clear to everybody. So notice that very easy for me to translate between here because of the definition of the Fibonacci number being recursive like this. So I thought I would show you how it might play out if you were to try to actually compute this. So remember that there's 2 recursive calls that happen. So suppose I'm trying to compute the 5th Fibonacci number. So that means that there's going to be 2 recursive calls that happen. One that is fib of 4 and another that is going to be fib of 3. That's because I take the input, I decrement it by 1 here, and I decrement it by 2 here, making these are 2 smaller problems. Likewise, when I have 4, I do 2 recursive calls because the input isn't small enough for which I know the answer. Now, like I mentioned to you before, if for a sufficiently small enough answer, I just want to solve it directly, I can. I could have redefined this algorithm, or I've given you many more base cases where, say if I wanted to go up to 8 or 13, like we were doing a moment ago, I can do that. But these will all be base cases for my recursive algorithm. So that brings me to another point in a little bit. So each one of these, I have 2 recursive calls until it either becomes fib of 2 or fib of 1, right? And in that case, I can compute the answer directly. Now, I haven't really quite described what this might represent. It's just the overall execution of all these recursive calls. Some people would refer to this as a call tree, but I haven't defined a tree yet for you. We'll talk more about trees a lot later on in this course. So for those that are curious, some people call this a call tree, but I haven't really defined what a tree is quite yet. We'll get there later on in the course. So the point here is that, there's a lot of these recursive calls that are going to happen. Now, perhaps there's a lot more than maybe we would like to happen. I want to ask you, based on what you see in this tree, to compute the answer, does anybody see anything that I'm doing here that maybe seems rather inefficient? Any ideas at all? So remember, to compute fib of 5, I have to do all of these recursive calls until I get eventually these, and I can combine those answers, just like I did last day when I was considering my case when I was summing them. But now I have 2 recursive calls, so all that's happening is now I'm going to take both of those answers, combine them together by adding them, and I return that as the result. But does anybody see anything about this that just really I don't know. I'm one of those people that, like, the minute you see something that like there seems to be something I'm doing here that's really just inefficient. Now, this is just what the algorithm does, right? But does anybody have any suggestions of something I might be doing a little bit more than maybe I should be? This is more of just meant for just discussion. We're not going to go too deep on this. I talk more about this in 340, but I thought it would be something we could just talk a little bit about. So when you look at this call tree, so remember, this represents the recursive calls, all these function calls that are happening. What do you see a lot of happening? There's a lot of repetitive calls, right? Does everybody see that? There's a fib3 here, there's a fib3 there. There's fib2, fib2, fib1, fib2, fib1. There's a lot of, it seems like it's doing a lot of things multiple times, including fib3, right? So this is actually a good example where recursion may not be the most appropriate way of trying to compute the nth Fibonacci number, even though I wrote it recursively. So I'll give you a little bit of intuition behind this. So notice that everywhere I do recursive calls, so I have 2 of them, right? Notice that if I look all the way down the leftmost side, every time it goes down by 1, 5, 4, 3, 2, and then when it hits 2, I can actually just compute the answer, right? So notice every single time until it reaches fib of 2, it splices off into 2 recursive calls. It creates 2 recursive calls, right? So if you think of it like that, every single time I do one of these calls, so if I start off with 1 call here, so I have at most 1 call that happens here. There's at most 2 calls that happen here because each time I have 2 here. So now I currently have 2 recursive calls that happened, right? Okay, so at most there's going to be 2 that happen, right? For each one of these. There's at most 4 calls that are going to happen at each of these respective sizes. I've drew it like this deliberately so you can see this pattern that I'm going to have here. Now, suppose that I made the input of this bigger, just for the sake of discussion here. What would happen is this one whole thing might still have calls that are going to keep happening where it splits off into 2. One side of this tree, this structure is going to eventually reach fib2 and fib1 faster than the left-hand side. The right-hand side will cease faster than the left-hand side. This is because it always goes down by 2. So notice that if you look at the number of function calls that happen, it's actually going up by powers of 2 as an upper bound on it. Does anybody see that? So every time it's just doubling the number of calls that happen. At most. Keep in mind there is a sharper bound on how many are happening, but I just want to give you an intuition for this. So at most, eventually you're going to get down to when it's fib of 2 or fib of 1, right? But the leftmost side is just going to keep going until that happens. So does anybody have any insight maybe on how long this algorithm might take? Now keep in mind, if you look at 1 call of this function, notice that if I were to just ignore the recursion here, and I just pretend that these were constant operations, notice that this whole thing, this 1 function call, takes constant time. If I ignore the recursive calls. Does everybody see that? So the way I can argue this is notice that, okay, well, if I ignore all the recursion, every one of these operations takes some constant number of time, right? So all I have to do is figure out how many function calls happen. Does anybody have any ideas of what the running time of this is in terms of big O? Any ideas at all? I just thought I would just throw this more as a fun discussion point. Any ideas? So somebody's suggesting quadratic. So that's one suggestion. Are there any other suggestions out there? I got another one for 2 to the power of n. Any other suggestions? I got another 2 to the power of n. So I have a question. Anybody, so I know that there's somebody suggesting a quadratic, another person suggesting an exponential. I want you to look at this tree very carefully. Notice that there's at most one function call that happens here. This takes some constant amount of time to happen. Each of these takes constant time, but notice that there's 2 of them. Then there's 4 of these, but remember, for the total execution of the algorithm, I eventually have to reach the base case, but that has to happen for all my function calls at some point, right? So if I want to know how many operations are happening in total, it's actually based entirely on how many function calls there are. So it's just simply the sum of how many there are, if you think of it like that. Now, this isn't a sharp bound on how much it is, but most certainly it is true that the worst case time complexity is, in fact, big O of 2 to the power of n, which is slow. In fact, you can get more tight with this. If you know, for example, the golden ratio, there's this constant called the golden ratio. You can actually show that it's the golden ratio to the power of n, but that's beyond the scope of this course. But you can have a lower bound on it of big O of 2 to the power of n over 2 at least, and at most being big O of 2 to the power of n. But the big point here is it takes exponential time, regardless. So this is where thinking things recursively is helpful, but most certainly in practice is not efficient. Does everybody see that? So do you see that I'm doing a lot of repetitive work here? So another suggestion I can have, and I talk a little bit more about something like this in 340, is, or at least it's something pretty commonly talked about, is notice that I know how to compute the nth Fibonacci number, right? So suppose I use an array instead. Say I put the first 2 spots, I put the first 2 Fibonacci numbers in there. Suppose I have a loop, like a for loop, instead. Could you tell me how you could compute the remaining positions in this array, given the fact you know the first 2? So if you create an empty array, you fill in the first 2 being your 2 base cases, Fib1 and Fib2, you could actually just use a for loop, right? You just add the previous 2, exactly. So if you use that information, you can actually compute the nth Fibonacci number using some additional memory, using an array. You can actually compute this actually much faster. You could do this in big O of n time, which is considerably faster, right? So sometimes thinking of things recursively is helpful. Other times thinking of things iteratively or using iteration is also helpful. So those 2 things, I want you to think about it more like there's a couple of different ways you can think about the same manifestation of a phenomena. So in this case, Fibonacci numbers, very recursive intuitively, but most certainly if you think about it, we actually know how to compute it, right? You just take the 2 previous terms, you add it together, just like what we did at the beginning. You can do the same thing with just an array. And it's much faster. Notice I'm not repeating any work when I do this. Just like I'm doing over here. I don't want to do a lot of this extra work. I talk a little bit more about some other ways you can optimize recursive algorithms so you don't have a lot of this repetitive work. A technique called memoization comes to mind, but that's beyond the scope of this course. But no, I just thought I would have a discussion with you about Fibonacci numbers and how this might influence the time complexity a bit. But we're going to definitely go a little bit more basic than just this. But are there any questions about my Fibonacci number example here before we proceed? This is just meant to just be mostly a discussion, so we could bounce some ideas back and forth so that I can talk a little bit more about how recursion actually works. Because up to this point, we just know that there are these function calls that happen that are of the same name and signatures. Just I change the input, right? So it's just I make the input smaller. And the whole idea is that I need to make it smaller so that I eventually can solve the problem, because I know how to solve the problem when it's small enough. So I must stress that it doesn't have to be necessarily that it gets smaller, it's just that it has to be formulated in a way that I answer the problem at some point. that's another thing to keep in mind. So for example, if I want, like in my example where I was counting numbers, I could have counted down or I could have counted up. So why don't we talk a little bit more about how recursion actually works? Because at first you might say, Dan, all this stuff, like where you have these functions, like they're the same name, right? Like, is there like something going on here that's special about this? And here's the neat thing, is the answer is actually no. So anything you know about a function call just as applies and it's applicable to recursion, at least on a computer. So it's just, so if you think of recursion as some very special thing, it is not. It's just a function call. It's just that we're using the same names. It's just the technique is what makes it unique. So let's talk about this. So you're going to find that a lot of what I'm going to say is just as applicable to functions. It's just that I'm going to walk you through the process for how we use function calls to do recursion. So watch this. Watch this. So the big mechanism, as I suggested last day, is that it uses what we call the call stack, which is also sometimes called the runtime stack. So this is very often used, well, at least on computers, it's used to store data needed for methods and functions while the program is running. So you may have, for example, heard of something like stack memory before. This is the same thing I'm referring to here. So with each of your function calls, we're going to have some additional things that get stored along with this. Why? Because for each function call, each one has its own declared scope. And for each one of these may have their own variables that have their own values. Just likewise, when they're a function, they return something, they also have their own return value, right? So these are all things unique to a given function call that are stored along with this call stack. So things such as the parameters are stored, local variables. So that means that each time you make a function call, that means that if you have local variables for that given function call, so like if you have a variable called x in your function, each time you call that function, it has locally stored its variables. So that when you use so this is one thing that often catches students at first when they think of recursion, is they think it because it has the same name, it means that they have the exact same local variables. And the answer, of course, is no. Even though they have the same names, they're actually two separate function calls. They have their own stored values for the local variables. This is one thing that commonly catches some students. The return value. And the bigger thing, now I'm not going to focus so much on this part. This is something you might learn a little bit more about in a computer systems class. Say if you're thinking about things like assembly or anything like that, the memory address of where to return, of where to continue executing. So for us in our discussions, what this is just saying is, hey, look, when I'm done performing my function call, where do I resume from for my continuing execution of the program? So for example, if I made a function call within another function, I want to know what instruction do I have to resume when I come back. That's what I'm referring to here. So the big thing for us is that every time you make a function call, it creates something called an activation record, which is sometimes called a stack frame or call frame. That's a little squeaky. Whenever a function or method call occurs, an activation record which naturally has several different names. So sometimes called a stack frame or call frame. We call it a frame because you think of it like a window. So imagine like I'm looking out a window. Each time I make a function call, you imagine I'm peering into what is necessary for the function call to happen, like I'm looking through a window. Or just think of it as a frame, as a perspective. I'm thinking something like physics, for example. You might think of a frame of reference. The same idea is here. So that's why the word frame might be much more suitable for certain circumstances. And also, if you don't like the name activation record, these are also same names for the same thing. So when you make a function call, what it actually happens is it gets pushed onto this call stack. Remember we talked about what a stack is, and we push elements onto a stack? That's exactly what's going to happen. An activation record, for some reason I put an S there, an activation record is created and pushed onto the call stack. So the big thing with us is that this call stack is a part of the runtime memory. Just like there's this thing called heap memory, there's stack memory and heap memory. You may have heard of these terms before. If not, that's not a big deal here. Well, certainly the stack is the thing we're going to focus on here. These are all parts of the runtime memory. So the big thing I want you to know about is whichever function is at the top of this call stack is what's currently being executed. That's the big thing. The other thing is that when the function finishes and completes, then it gets popped off the stack. So just remember we talked about pushing and popping? Same idea here. So I'm losing my friends. When a function completes, it is popped from the call stack. So whichever's at the top of the stack, that's the function currently executing. Oh, I knocked over my green friend, unfortunately. So I thought it would be a good idea we kind of walk through an example of doing this using one that we talked about last day, so that you can really see that what I draw on the board actually is really not that much different than what actually is happening. So first, just want to make sure everybody's familiar with the idea of a stack. We talked about that near the beginning of the class, but in case anybody's not sure, I'm going to do an example. So I'm going to come back to last day. We'd seen how we can recursively add numbers from 1 to n, right? So what I did was I started at n and I went down to 1 and I just added them that way. So I had this function called recsum. So I'm going to just walk you through the process of that execution. So let's talk about this. So let's do an example. So I'm going to be using recsum from last day. So the first thing you need to remember is that, at least that we're familiar with, when we execute our programs, there is a function that we initially call. Can somebody tell me, what's the function that we call first? Whenever we have our C++ programs, what's the function that gets called first? It's main, exactly. So you know main is going to be sitting right here. That's the thing that's going to be on the top of the stack right at the beginning of the execution of the program, right? So like I said, this is how functions just behave when you call them. What's going to be different with us is just that we're going to have functions that just use the same name. So as soon as you understand that, all of this is just demystified entirely. So I start off my execution of the program. I start off with main. Now imagine that main calls recsum of 4. So let's look at our example. So let's take an example of rec sum of 4. So just to remind you, last day we did actually an example kind of like this one, where to compute the recursive sum, we add whatever the input is plus the recursive sum of that input less 1, right? So just to walk you through this process without us getting to the call stack quite yet, actually, let's do it. Let's do that. Actually, let's go step by step through this whole process. So let's start off. Imagine that there's first and initially a call of rec sum 4. So just for the sake of space, I'm going to write the function's name and their parameters on the left-hand side. So rec sum 4, it has input, so it has its own copy of the parameters, the values that are parameters, and the local variables in the algorithm. In our case, we don't really have any, so we would have them all in here, though. And we'd have a return value that comes out of this thing so that I can pass it along back to where the original function call happened, so whatever the program needs to use it, they have the return value. And they can do whatever they want with it. So I don't know really what the return value is quite yet. I just know it's some integer, right? So what happens? Recursive sum, what it does is it goes, whatever the result will be in this case, because it applies the recursive case, it takes whatever the input is, n, but remember n here is 4, right? So it's 4 plus, and it does a recursive call. Recursive sum 3. So what does that mean? That means it's going to call recursive sum. For recursive sum 4 to complete, it has to actually finish and return whatever the result of this line is. Does everybody see that? So to compute rec sum 4, I actually require the result of rec sum 3 to actually finish the completion of that function, right? So what happens? I call that function. It goes on to the call stack. And I will not continue computing rec sum 4 until rec sum 3 is finished. Whichever function's on the top of the stack. So now I have rec sum 3. Remember, its parameter, its input here is 3. Like I said, any local variables, it will have its own set of local variables that of the same name that whichever function call, like if it's the same name, it has local variables of the same name, but their values might differ. But they are, like if you modify, say, if there was a variable called x inside of, say, rec sum, and it depended on n, it doesn't actually get modified between the two function calls. Each has their own. That's a common mistake that some students make, is they just assume that, oh, the variable just magically changes between the two. No, it's just a function call. Remember, just think about scope. So just think of the scope of the variables. So when you make a function call, when you call that function, it has local variables that are assigned to certain values. And the big thing is that each one of them has their own set of local variables, its own set of values for those local variables. So anyways, I don't really know what the return value is quite yet for rec sum 3, but to compute rec sum 3, it's 3 plus rec sum 2, right? So it calls rec sum 2. Again, the same idea. And when I do call rec sum 2, it's 2 plus rec sum 1. Well, rec sum 1 gets called. But here's the thing. In rec sum 1, does it go to the recursive case or the base case? It goes to the base case. So now the big thing you really want to catch on to when you're designing a recursive algorithm or implementing a program that uses recursion, the big thing is that you want a whole definition of how to solve the problem. So the base case is kind of like that last piece you need to put everything together. Since I know how to solve rec sum 1 directly, I compute it. I just simply say, hey, look, the answer is 1, so I'm going to return 1. And here's the thing. When I do that, I'm going to return 1. So I return 1. As a result, of computing Recsum 1. And what happens at this stage is this activation record gets popped. So it's done, right? So now currently Recsum 2 is on the top of the stack. And it knows where to go, because the last part I talked about here, the memory address for which it needs to continue executing, it knows exactly where to go. So Recsum 1, of course, is just 1, right? So it'll come right back to this line that we needed where we compute 2 plus whatever the result of this is, and it can complete that arithmetic operation, which gives us 3. So it figures out, oh, hey, look, the return value is 3. I'm going to return 3 now. So now the answer to this is sorry, I'm getting a little ahead of myself. It's this right here. It's 3. Now Recsum 2 is done, popped off the call stack because it finished executing. Now I'm doing Recsum 3. It's 3 plus 3. Just 6. It returns 6. It'll resume back to performing this operation because it was in the process of computing this, right? So I take 6 plus 4. This all together, that's 10, right? And Recsum 4 completes. It pops it off the call stack because it's finished. And now we're back to our main function. And then the main function will continue to proceed until it completes. And it may use this 10 however you see fit, but that will be the result in that case. And then the main function will cease at some point, concluding the execution of the program. So do you see that really this isn't really anything crazy or special? It's just functions. So how's that, everybody? Are there any questions about that? So if you're curious about this whole process I went through, in the notes I actually will have a step-by-step process of this if you need to remind yourself of how I went through this entire thing written down literally. So I literally go through everything I just said verbally in the notes if you just want to go through this step-by-step yourself. But just the big thing to remember, the recursion first is just another way of thinking about how we can solve different problems. Some problems, they're very natural to express recursively. Others, maybe not so much. But the point is that you got to look at iteration and recursion like they're mirrored. They're not necessarily mirrors, but they're definitely alternative ways of viewing the same thing. So whatever you could do with iteration, you could do with recursion and vice versa. Just sometimes it makes more sense to think of things recursively, other times it makes more sense to think of them iteratively, or at least in practice. So I want to give you some tips on how to think about designing or implementing recursive algorithms. So I want to give you some quick tips. But yeah, that's all I have to say about how recursion works. It's just using the call stack here. It's just like when you run any other program where it calls functions. So here's some tips. The first one is ensure you have an appropriate base case. That's the first thing. Remember, like I told you, the whole idea is that every time you make a recursive call, the idea is that you want to make the problem a little smaller, whether it be you make the number bigger or smaller. The point is that you make the problem smaller, so that eventually you'll reach this base case. Now, if you don't do this, does anybody have any ideas of what that might cause? And I'll give you a hint. So if I have something like a while loop, and say I have a variable called x and I assign it to be 0, and say I just have it where I require that x is less than n, and say n is just some other input that I get, but it's some positive integer. What would happen with this while loop if I don't modify x? It goes into an infinite loop, right? So here's the thing. If you don't make sure that the problem instance you're considering is getting smaller in some way, you might have the same thing happen. Now, you might ask, okay, so what does that mean? Well, it means that you're going to have it where it's just going to keep repeatedly applying the recursive case over and over and over and over again. And actually, one little thing I'll give you as a fun little insight into this, if you ever find yourself thinking about iteration versus recursion, one way you can think of how you can simulate iteration using recursions, you can almost think of it just like what I just described, where you'd imagine you have a recursive call that's mimicking the while loop or a for loop where it decrements or increments the variables. So that's actually theoretically how, if you say take a class in programming languages, you might learn a little bit more about what I'm talking about. But that's beyond the scope of this course. But most certainly, it's a very interesting little detail. And actually our examples, and this is actually why I showed you some of my earlier examples, is actually all of them do this. So if you actually look at the iterative version versus the recursive version, some of the ones like we were counting and summing, they actually do just this. So you have to keep in mind that you got to make sure you have an appropriate base case. You don't want to have it where you miss the base case. So if it gets too small and it skips right past the base case, it might go into an infinite loop and may never terminate. With one small detail that it does really matter. It'll fail to terminate if you miss a base case or don't properly define the base case. Another thing that I want you to be aware of is that if your recursive algorithm uses too much memory, and in particular I'm talking about the stack, uses too much stack memory, which, must I be very clear, the example we just talked about is one case where this can happen. Which stack memory or never terminates, it causes something. It causes this phenomenon that you may have heard of before. If you find yourself ever going on the internet, you're looking up, like, how do I do this in C++? You'll find you'll run into like a website. Yeah, Stack Overflow. That is actually what this is called. So if you ever wonder what Stack Overflow is, that is what I'm talking about here. This is exactly what that is. It never terminates. It causes a stack overflow. So if you ever find yourself really wanting to play around with this, try taking one of the examples I've given you, where, like, say we're doing the recursive sum, like our recursive sum example. Instead of having it where it decrements by 1 on every time, just have it where it just takes n again. And I encourage you to make it so it has a print statement and see what happens. Yeah, what will happen is we'll run out of stack memory. Yes. So some languages, they'll actually throw an exception at you and say, hey, look, you're using too much stack memory, man. Or you ran out of stack memory. Yeah. So yeah, you'll just keep, because remember, every single time I make one of these activation records, this is actually something interesting that I haven't really said much about, is that every time you make one of these function calls, each one has a copy of their local variables, right? And so say if you use memory in each one of these function calls, if you have a whole bunch of function calls, the total amount of memory that your algorithm uses is heavily dependent on how tall this stack gets. So if the stack gets really, really, really tall, or what we would call in recursion, it's a very deep recursion. If this stack gets very, very tall, you're going to end up using a lot of memory. So what happens when you use too much memory is that's what we call a stack overflow. Some programming languages will literally call an exception called the stack overflow exception. But I encourage you to play around with this. It's really a lot of fun. So this is when the program runs out of memory for the call stack. Hence its name, right? So usually in C++, what will happen is you actually do get an exception thrown, or it'll just start accessing parts of the memory that you weren't anticipating. Other programming languages will throw a deliberate exception because it's being a little extra careful for you. Other languages, like in C++, the expectation is that you understand that, like, if you use too much memory or you go out of the bounds of some structure, you might be accessing something you may not want, which will lead to a seg fault. So in practice, when you run into these circumstances, sometimes it will be where it gives you an explicit error of a very similar name to this, or it'll give you a seg fault because you'll access something that's just outside of the bounds of the stack memory. But one thing I do also want to mention, I like to make sure I mention this, is that compilers are often optimized to optimize recursive code. So sometimes it is actually just appropriate to use the system stack, because the system stack is optimized for things like function calls in a lot of languages. Some not so much, but some others most certainly. The other thing is that many of the recursive algorithms that, as you've seen, you can actually rewrite using iteration. Now, as I mentioned, you can do this with any recursive algorithm, but most certainly the ones that you would really like to do this with for further optimization in practice is try to avoid having it where it tries to emulate the stack, and it's more so that it actually is just performing the operations within the confines of one function call. So you can actually simulate this call stack if you wanted to, but it sort of gets away from using the system stack, which is better optimized to handle recursive code. For example, there's certain types of optimizations that occur with a compiler, which I won't talk about here so much, but there's certain structures that recursive programs can take on. There's something called, for example, tail recursion, which actually is very similar to what a loop does. And for these types of recursive algorithms, compilers are often very well adept at optimizing those things. But I feel like I just wanted to mention this, that the recursion itself in practice is sometimes something that works to your benefit if you know how to optimize it carefully. Other times, it may be better to think about how you might turn it into an iterative algorithm as opposed to a recursive one. But for us, you'll find that thinking of things recursively is very powerful because one, it simplifies the ideas down, and two, even though you can actually straight up implement them, you have to be very mindful of the fact of how deep the stack can get and how deep you want it to get. So just be mindful of this. But yeah, no. Are there any questions before we proceed? I thought I would mention, while you're thinking of any questions, I did include another example that you're encouraged to. I encourage you to try out. It actually is some code if you're curious about it. How to recursively sum an array. So I would argue it's a pretty cute example in the notes for recursively summing over an array. One thing I should point out to you, and this is just as true with any other function call, one thing I got to warn you about is when you're doing recursive calls, usually I recommend, if you have complicated data structures, pass by reference or by pointer as opposed to copy the entire thing, unless you're dealing with primitive types. The main reason why is because every time you copy, you have to copy that, and it's stored in each one of the activation records, right? You can either store a pointer to it, or you can actually copy the entire thing. Sometimes it's appropriate to copy the entire thing. Other things, you might actually just want to manipulate the data structure itself. So one thing I wanted to point out is that if you're thinking about the amount of memory or extra space that gets used, I'll usually presume if we're dealing with something like an array or some other data structure or container or collection of elements, normally I'll just assume we're passing by pointer or by reference. So just keep that in mind. So a question, what would be an example to use recursion over iteration? So there's a couple of things. So one thing, as I mentioned, a lot of compilers are optimized to handle a lot of different common patterns for recursion. So very often, just communicating the algorithm and using recursion, well, it's simpler. It often, well, I would argue it's, for a lot of the things we're going to see, especially later on in this course, describing them recursively is actually a lot easier to do than their iterative counterparts. You can, of course, go through the exercise for all of these algorithms and do that. But most certainly you'll find that really you're not losing a whole lot by doing that. Because remember, at the end of the day, programming languages, they're meant to help humans communicate tasks to computers and also among other programmers a lot of the time. So at the end of the day, if the compiler is anyway going to optimize that code for you, does it make any much of a difference if you try to optimize it yourself? That's one thing I would argue to you. That's something I would encourage you to think about or even debate among other people about, because it is something that is hotly debated. Is some people are really, really passionate about, hey, look, I don't want to see a single lick of recursion in my program. Some people are like, yeah, bring on the recursion. But most certainly the biggest thing I do want to point out to you is that when you have a very deep stack, like if this stack got very, very tall, that might be a case where you might want to choose using iteration over recursion. But when you think about recursion over iteration, you'll find that a lot of the algorithms I'm going to present to you, especially for some of the more recursive structures, like these things I'm going to call trees, the algorithms are much simpler to implement recursively. And the thing is, when you actually look at the patterns they take on, many of the times it's just something that a compiler could optimize a little further. But yeah. I would argue that the recursion benefit is just that some languages are just built for recursion and optimizing, others not so much, but you'll find that it's very much a depends kind of circumstance. But for us in this course, the recursion will be beneficial because it makes it easier for us to describe the algorithms. And sometimes it'll be very natural. But hopefully that answers your question. But yeah, you can go really deep into this topic. But yeah, just be mindful of because keep in mind, if you have a lot of memory that gets used by each one of these, maybe it might not be a good idea to use recursion in practice for it. Instead, maybe choose to try to find some way to do it iteratively. Sometimes that is not a trivial task, by the way. That's sort of why we want to talk a little bit about this. But yeah, no. So feel free to take a look at that one example I gave you there. Like I said, I thought I would show you an example of the same idea I did the other day, but over an array. So that you have at least one example where you do it with a data structure. I encourage you actually, if you find yourself curious about that one example, try doing it with a linked list instead. You'll see that the pattern is very similar. It's just that instead of having it where you go to the next index, you just go to the next node. So I thought I would switch gears for the rest of the lecture. We'll talk about something that I know you've seen before. If not, I know that you've seen the basics of. It's something called binary search. So I want to talk a little bit about that and contextualize it in terms of recursion. So let's talk about binary search. Because I think it's a really good example of this iteration versus recursion and what kind of benefits you can have one over the other. And just generally how one actually can make it a little bit easier to communicate the algorithm and analyze it versus the other that might be a little bit more practical. In this case, you'll find that the recursive counterpart makes it easier for us to analyze the algorithm and better understand it. But you'll find that the iterative counterpart is performance-wise the one that you might want to go with because it uses less stack memory. At least if you have a very big array. Okay, so let's talk about binary search. I'm just going to remind you about how binary search works. For those, actually, is there anybody who's never heard of binary search before? Don't be shy. It'll help me know if there's anybody out there that I need to remind people about this stuff. And that's okay. The great thing about binary search is I would argue it's very elegant. There's a lot of theoretical things you could say about binary search and its relationship to the search problem. So let's talk about binary search. I thought I would contextualize that with our examples here. Okay, I think we're pretty much doing okay here. So I just want to remind you of the idea that we had for binary search. So just as a reminder, remember we talked already about linear search. So the idea is that I have an array and I have some element or key that I'm looking for. In linear search, I scan from left to right through my friends here. And if I find them, like I said, for example, I'm looking for the green car, sort of a little bit bluish, but most certainly it's greenish enough. If I'm looking for the green car, I can scan from left to right. If I go through all the elements, I can guarantee I can do that. So you might know that there's actually a faster algorithm if I know a little bit more about the array. For example, if I knew that all my friends were listed from shortest to tallest, say if I wanted to identify a friend based on their height, what I could do is if I knew that my friends were ordered by their heights, let me just move them up a little bit. Actually, let's move them back down. I was about to lose my lion friend here. We don't want to lose our wicked dinosaur friend here. So I'm pretty sure the car is shorter than the lion. The dinosaur, I think, just because the horn is a bit taller. It's like heels. If you can get away with it, do it. I'm just joking, of course. We got the cowboy friend and we got our lovely green friend here. So notice I've listed them out. I believe I've got them listed from shortest to tallest here, right? So if now I was trying to seek out a friend based on their height now, does everybody see how binary search can be accomplished here? So instead of starting at the leftmost side, I'll start in the middle with a guess. And what I can do now is I can ask, okay, have I encountered the green car? Say if I'm looking for the green car, for example. If I've sorted them from tallest to shortest, and say if I'm looking based on their heights, I can compare, is the one I'm looking for shorter or taller? In our case, it's shorter, right? So I don't have to look anywhere to my right here. Because my lovely green friend and my cowboy friend, they're taller than the person I'm looking for. And yes, cars are people now. It's the eyes. Don't ask me how this works. I'm just joking around. So now I know that if I've examined the dinosaur and everybody to my right, I already know that, sorry, I don't have to even examine them. I already know that they're taller. I just examined my left half here. I can look at this. I can say, hey, look, I have the car. Hey, look, there's the car. I found it. I'm done. I don't have to look at everything in my array if it's sorted already. So just a couple quick remarks before we talk about binary search. So we know that linear search solves the search problem in big O of n time, right? One thing I do want to make a remark about is that if I have no information about the input array, say it's unsorted, and I have no information other than that, linear search is actually the best you're going to be able to accomplish for the search problem. You might ask, how is that possible? It's because if you think of it this way, imagine I imagined an algorithm that could run better than linear time. So suppose I gave you some sequence of choices that could happen. The idea is that whichever sequence of choices you make, somebody hypothetically could easily put the key that you're looking for in a place that you did not examine. And that's actually one of the things you'll notice about linear search, is linear search works because it examines every one of the elements, right? In the worst case. So in the worst case, you have to look at all of them. That makes sense because you have to look at the entire input. But most certainly, if you're curious more about this, often when I teach 340, I will actually prove this to you. We'll use something such as something called an adversarial argument. It's very similar to the idea I just explained just now. But if I know the array is already sorted, so if I know the, however, in the special case, where L is sorted in non-decreasing order, we can use binary search. So now I'm going to describe binary search. But remember, we need to make sure the array is sorted before we can use binary search, right? You can't just obliviously use it on an unsorted array. You'll have to sort it first. This is because binary search uses the fact that I have so if I ever make a guess, I know what's happening in whatever half I discard. So this notion of discarding halves is actually something that's very natural to describe recursively, which you're going to see in a moment. Because in the iterative counterpart, as you might know, you have a lower bound variable and upper bound variable. You're going to have the same thing here for the recursive counterpart. But when I talk about halves and so on, I'm talking about halves. But I don't need to just straight up create a whole new array or anything. I'm just going to use the same thing. You notice that in the iterative counterpart of this algorithm, you'll have a lower bound, upper bound. I'm going to have the same thing here. But you're going to notice I'm just going to use recursion to describe how I'm going to take this process and which half I'm going to use. In fact, if you go through the same exercise we did about how we looked at iteration versus recursion, if you look very carefully at how I'm going to describe this recursively to you, you can actually see that you can apply the same idea to create the iterative counterpart you may have seen in 115. So question, couldn't the array be sorted in decreasing order and still use binary search? Yes, you can. Just be wary that I'm using the word non-decreasing because what I care about is that the way I can compare them is either going to be less than, equals, or greater than. Non-decreasing is just a broader class than just decreasing. Actually, sorry. Non-decreasing. No, let me just rephrase that. I was thinking a little ahead of myself. All you'd have to do is just change the comparison. Sorry. So instead of it where you check, so remember, the larger half and the lower half, all you'd have to do is just change the presumption of which direction you would discard. The left half or the right half, you just discard the right half instead of the left half. But yeah, I must stress that it's very natural. It's just the point here is that I'm just trying to keep it simple where we think of things as smallest to largest, but you most certainly can adapt the algorithm for largest to smallest. So here I'm going to describe the recursive counterpart. I must stress that very often when people describe recursive algorithms, they have something called a driver function. So what it'll do is it'll have the exact parameters of the problem itself, and then it calls the recursive counterpart of it. So you'll see an example of it actually in the notes. So after class, I will post actually some C++ code for binary search, and you'll actually see what I'm talking about with this driver function that will do it'll initiate this recursive call. So I must stress that the initial call will be, and I'm going to have a lower bound variable called L. I'm going to start it off at 0, and the upper bound U is going to be n minus 1. So I'm going to have my algorithm here. It's going to be called binary search. It's going to have the array L. It's going to have the key X. It's going to have lower bound L, so lowercase l, and upper bound U. So the first thing that's going to probably strike out to you is going to be how brief my algorithm, well, the description in recursion terms, recursively, I'm getting very excited about this. You're going to see how much more brief the recursive counterpart is to its iterative counterpart very shortly. So input, I have the array L, I have the value X, I have the lower bound L, upper bound U. And they serve the exact same role they do in the iterative counterpart, just to be clear. And the output, same thing I had before for linear search. And I must stress that, remember, this array L is under the assumptions I've given over there. So output, we get a position I, such that L sub I is equal to X if X is in L and minus 1 otherwise. Okay. So watch this. So, you know when we do binary search, you got to imagine it like I'm examining my array, and every time I take my array and I discard half of it, I'm not literally discarding, it's just conceptually I'm discarding it by changing these values for L and U. Every time I do this, it's going to make the number of elements I have shrink. It's going to get smaller, the number of elements I have yet to consider. When I run out of elements to consider, I'll have no more elements to consider at all, right? So if I fail to find it, it's going to be that L and U cross over each other. And the same thing happens in the iterative counterpart of this algorithm. But watch this. This is actually going to formulate the base case for its recursive counterpart. So if L is greater than U, so this is when the interval crosses over itself, you just return -1. So this is your base case right here. So that's one base case. Just to be very clear, there is actually technically two. Just in binary search, it's easier for me to break it up in these two pieces. So this is base case number 1. Otherwise, we know that it hasn't crossed. We have at least one element that yet to consider. So first I perform my guess, just like you would usually. So I'm going to compute L plus U divided by 2. I'm going to make sure it gets rounded down. Now, as you might know, if you're using type int, it always rounds down. It doesn't keep track of any fractional part of the numbers. So when you're actually implementing this, you don't actually need to put in a floor function yourself. Integer arithmetic already does this for you. So now I check if L sub mid, so I check my guess in the middle, is equal to X. In this case, then I return mid. So this is base case number 2. Because there's two possibilities, right? Either I find the position or I don't find the position, right? Otherwise, we have to examine one of these two halves, right? Otherwise, L sub mid is less than X. So we check if L sub mid is less than X. If that is the case, then you're going to return the result. Then we're going to return the recursive call, whatever the result of recursive call binary search, or I give L, X. I change whatever the lower bound guess is going to be to mid plus 1. And I'm going to have upper bound U still intact. You might ask, Dan, why is this the case? It's because my guess was too small. So that means I'm going to have to consider my taller friends, just like I have over here. Say if I have to check to the right of the dinosaur. Otherwise, we check the left half, right? Otherwise, we return binary search. Where I give L, X, keep the lower bound L, but now the upper bound is going to be mid minus 1. You might ask why there's this -1 and +1 business. Just for the sake of reminding you, we checked actually L sub mid already, so we don't have to consider it again. It technically shrinks the input, well, it makes the problem smaller by at least one element each time. So that makes sure that there's at least one element we're not considering anymore. This is actually one way you can actually prove that binary search terminates in finite time. But yeah, so that's binary search and its recursive counterpart. So you can see that these two right here are your recursive cases. So based on what you see here, is this much shorter than the one you may have seen in 115? Well, it seems a little bit more like, some might argue that this is a little bit more elegant because, now keep in mind, binary search itself is an elegant algorithm, so it doesn't really like, its iterative counterpart is very natural to describe too. But most certainly this is very compact, right? So notice that all it's doing is just carrying out the same idea I talked about here, but it's literally like it's doing it. But now notice that all I'm doing is I'm just passing along my array, and the only thing that gets modified are these lower and upper bounds, just like its iterative counterpart. So that being said, let's start talking about how we can analyze this algorithm. So just as a reminder, just to be very clear, if you were to actually use this algorithm, you would actually have a driver function. Maybe it's called binary search, but its parameters are just like L and X. And it will call this algorithm binary search, where you make L be 0 and U be n minus 1. And that's what's going to kickstart this algorithm. So it'll just return whatever the result is of that. So I will have a full example in the notes of what I'm referring to here as this driver function versus the algorithm in question. So the reason why we call it a driver function is because it initiates or sets up the algorithm, just like a driver on a computer might. But yeah, no, so let's talk a little bit about this. So in the worst case, so question, what would be the worst case running time of this algorithm? You may have heard of it. If not, we're going to well, either way, we're going to derive it ourselves. But you may know what the running time of this algorithm is. Does anybody know what the algorithm's running time is in the worst case? If not, I'm happy. We're going to actually be going through this very delicately. You might know it, you might not know it, that's okay. And I will tell you up front, it is better than linear time. In fact, this is very often one of the first examples you get to see of logarithmic running times. So I'm going to walk through how we might derive that. So for those that have never seen binary search before, I will include a full example of going through one instance of binary search. But for those that are already familiar with it, let's talk about how we can analyze it. So yes, so there's some people already talking about the logarithmic, some brought up some other ones. But the big point here is that we're going to see that this is going to be actually much faster than our linear search is. So let's talk about how we're going to analyze this. So I'm going to do the setup here today, and then we'll finish it up next class. How does that sound, everybody? So we'll kind of figure out how we're going to derive the complexity function together, and then we'll figure out all the nitty-gritty analysis stuff next day. How's that sound? So I'm just going to get a few things on the board here. So I'm just going to get this erased so that when we get over here, it'll be a little easier for us. Okay. So first, worst case scenario. Can somebody tell me what the worst case scenario is here? For binary search, what's the worst case? It's not in the array, exactly. Just like linear search. If X is not in the array, you're not going to find it. It's going to perform the maximum number of operations in that case, because every time I perform one of these guesses, I'm going to discard at least one element each time. In fact, it will usually be more than this. It'll be about half the elements each time. So every time it's going to discard about half each time of what all the current elements I'm currently examining. So every time it does this, discards about half, discards about half, discards about half. Eventually it's going to run out of elements to do this with. But the way you can maximize this is by just simply not having the element in the array. So when X isn't in the array is the worst case scenario. So our worst case scenario is just X is not in L, right? Just like linear search. So I must stress I'm going to include a much more thorough write-up in the notes. I thought it'd be better for us to just kind of walk through this in the same way that we've been doing lately, so we can count up the operations. So let's so usually when you're analyzing recursive algorithm, because this is in fact a recursive algorithm, correct? The first thing we're going to do is the same thing I talked about earlier on the lecture. first step we're going to do is we're going to ignore the recursion. I want to know how many operations are happening non-recursively, as in all the operations that happen at one given function call, based on whatever case it falls into. So a good idea is just count them all. So what I'm going to do is I'm going to first look at this algorithm. I'm going to first start off by ignoring the recursion. So the first step I'm going to do is ignore the recursion. So I'm just going to pretend that those are, in fact, just constant numbers of operations, because it's just some function call, but most certainly when you actually make those function calls, remember what I said about our analysis? These are actually subroutines. So you actually have to count their operations. So just like if you call any other function, you would actually have to analyze that algorithm too. But recursive algorithms in themselves actually have a really nice feature to them because we can actually see what kind of structure they give us. So the first thing I'm going to do is ignore the recursion. So let's analyze this algorithm where I'm just going to presume where you see a recursive call, I'm just going to assume it's some constant number of operations. So first, in the base case, notice that line 1, this first line here, takes some constant number of operations, right? Or it could be the case that it returns here, right? In either case, it's some constant number of operations, right? So in the base case, notice that it's just some constant number of operations. But if you just straight up just ignore the recursion, notice this if statement, that's some constant number of operations. Everything in here, if you ignore all of this, all of these take some constant number of operations in total, right? So notice if you ignore the recursion, the total number of operations that happen in one call is big O of 1. I'll let you look at the details in the notes for how I would split this apart if I wanted to go into more detail. But for the sake of time, just notice that if I ignore the recursion, all of this entire process takes constant time, right? Now, there are two parts to our analysis. I have a question for you. How many recursive calls happen? For one given call, what's the maximum number of recursive calls that would occur in one call? So just one single call? Is there like 2 recursive calls like our Fibonacci example, or is there just one? It looks like there's just one, right? So notice that if, say, this does, remember, in our worst case, X isn't in the array, so it's never going to do this. It's just going to check this, and then it's just going to go to the else if or the else, right? So here, it's just going to go, hey, look, either I'm going to go to the right or I'm going to the left, right? The right half or the left half. So notice that there's at most one recursive call that happens. So there's at most one recursive call per function call. So the question will be is how many function calls there are. Just like, when we see in our Fibonacci example, we've seen that there was an exponential number of them. That was very slow, right? Now we have sort of a grip over binary search. It probably isn't like that, right? So I want to put together a complexity function using these two facts now. So there's two parts to this. There's the base case and the recursive case, right? So the big thing I really want you to notice is that in the worst case, base case number 2 over here, it doesn't matter, right? It's never going to satisfy that condition. So its doubt is no different than if I just looked at that first if statement for the base case. So here we go. So there's kind of the two parts. There's the base case and the recursive case. We established that if you ignore the recursion, even if you counted all the operations, it takes constant time. So that means that if I consider when I have no more elements left, but no more elements, that is simply when n, the number of elements I currently have, is 0. So notice that we have kind of two things. I need a recursive part and a base case part. So our time complexity is going to be formulated as a what we're going to call a recurrence relation. So we know right away that the number of operations that when I run out of elements to consider, that's when the intervals cross on the first line of the algorithm, it performs some constant number of operations. Because it's big O of 1, I'm just going to write 1. But you can write big O of 1 or put another constant here if you want to call it C2 or C1. Also okay. I would recommend you actually put a fixed number here. So usually a constant would be more appropriate, or a 1. The point is, it's just some constant. Now, we know in the recursive case, we know that regardless, it's going to perform some constant number of operations, right? So that's the amount of non-recursive work that's happening when I ignore the recursion. Now I have to incorporate the recursion. So if n is greater than 0, what happens? Well, in the worst case, when I have at least one element, well, I have one recursive call that happens. So I'm going to represent this as another function call that's going to be of the same name, just like my recursive algorithm. It's going to simulate the running time. Now, I want to show you how I can come up with a nice bound on this before we leave here. So suppose that my guess here is mid right here. Say this is mid right here. So if I consider mid and say x is not this one, which is the case in the worst case, so I know it's not here, right? So that means that if there's n elements here in total, when I discard one of them, that's n minus 1 elements, right? So that means that regardless of the parity of n, whether it be even or odd, there's going to be at most n minus 1 over too many elements left when I do my recursive call. It'll either be on the right half or on the left half. If I do it on the left half, it will be that these elements will never be considered again. If it's on the right half, these won't ever be considered again. But the point is that this is an upper bound on how many elements I have left to consider. So this is actually the size of how many elements are left for me to examine at most. So when I look at my measurement of how big the problem is at this stage, it's just simply going to be how many elements I have left to examine. In this case, it's going to be at most n minus 1 over 2. I'm doing this actually as a sake of simplicity, as a simple way of arguing this. I'm going to argue that it's always going to be cleanly able to divide it like this, but it serves as an upper bound on the running time. If you want to get very technical about this, you would have floors and ceilings on either side, or at least a floor on one side, but I don't want to get into that detail. This will be sufficient for us. So anyways, I got to let you go. But when we come back next time, I'll talk more about this, and we'll do the analysis and find out what the worst case running time of binary search is. So I'll say thank you very much, and have yourself a beautiful day. I'll see you tomorrow.